Energy is being exchanged. Transferred. Released. In a great cosmic pinball game we call our universe. To see how energy stitches the cosmos together and how we fit within it, we now journey through the cosmic power scales of the universe. From atoms, nearly frozen to stillness, to Earth's largest explosions. From stars, colliding, exploding, to distant centers of power so strange and violent, they challenge our imaginations. Today, energy is very much on our minds as we search for ways to power our civilization and serve the needs of our citizens. But what is energy? Where does it come from? And where do we stand within the great power streams that shape time and space? Energy comes from a Greek word for activity or working. In physics, it's simply the property or the state of anything in our universe that allows it to do work. Whether it's thermal, kinetic, electromagnetic, chemical, or gravitational. The 19th century German scientist Hermann von Helmholtz found that all forms of energy are equivalent, that one form can be transformed into any other. The laws of physics say that in a closed system, such as our universe, energy is conserved. It may be converted, concentrated, or dissipated. But it's never lost. James Prescott Joule built an apparatus that demonstrated this principle. It had a weight that descended into water and caused a paddle to rotate. He showed that the gravitational energy lost by the weight is equivalent to heat gained by the water from friction with the paddle. That led to one of several basic energy yardsticks called a joule. It's the amount needed to lift an apple weighing 100 grams 1 meter against the pull of Earth's gravity. In case you were wondering, it takes about 100 joules to send a tweet. So tweeted a tech from Twitter. The metabolism of an average-sized person going about their day generates about 100 joules a second, or 100 watts, the equivalent of a 100-watt light bulb. In vigorous exercise, the power output of the body goes up by a factor of 10, one order of magnitude, to around 1,000 joules per second, or 1,000 watts. In a series of leaps by additional factors of 10, we can explore the full energy spectrum of the universe. So far, the coldest place observed in nature is the Boomerang Nebula. Here, a dying star ejected its outer layers into space at 600,000 kilometers per hour. As the expanding clouds of gas became more diffuse, they cooled so dramatically that their molecules fell to just 1 degree above absolute zero, the total absence of heat. That's around 1 billion trillionths of a joule. That makes the signal sent by the Galileo spacecraft as it flew around Jupiter seem positively hot. By the time it reached Earth, its radio signal was down to 10 billion billionths of a watt. Now jump all the way to 150 billionths of a watt. That's the amount of power entering the human eye from a pair of 50-watt car headlamps a kilometer away. Moving up a full 7 powers of 10, moonlight striking a human face adds up to 300 thousandths of a watt. That's roughly equivalent to a cricket's chirp. From there, it's a mere 5 powers of 10 to the low-wattage world of everyday human technologies. Put 10 100-watt bulbs together. At 1,000 joules per second, 1,000 watts. That roughly equals the energy of sunlight striking a square meter of Earth's surface at noon on a clear day. Gather 200 bulbs, 20,000 watts is the energy output of an automobile. A diesel locomotive, 5 million watts. An advanced jet fighter, 75 million watts. An aircraft carrier, almost 200 million watts. The most powerful human technologies today function in the range of 1 billion to 10 billion watts, including large hydroelectric or nuclear power plants. At the upper end of human technologies was the awesome first stage of a Saturn V rocket. In 5 separate engines, it consumed 15 tons of fuel per second to generate 190 billion watts of power. How much power can humanity marshal? And how much do we need? Long before the launch of the space age, visionaries began to imagine what it would take to advance into the community of galactic civilizations. In the 1960s, the Soviet scientist Nikolai Kardashev speculated that a Level 1 civilization would acquire the technology needed to harness all the power available on a planet like Earth. According to one calculation, we are 0.16% of the way there. This is based on British Petroleum's estimate of total world oil consumption, some 11 billion tons in 2007. Humans today generate about 2.5 trillion watts of electrical power. How does that stack up to the power generated by planet Earth? Deep inside our planet, the radioactive decay of elements such as uranium and thorium generates 44 trillion watts of power. As this heat rises to the surface, it drives the movement of Earth's crustal plates and powers volcanoes. Remarkably, that's just a fraction of the energy released by a large hurricane in the form of rain. At the storm's peak, it can rise to 600 trillion watts. A hurricane draws upon solar heat collected in tropical oceans in the summer. You have to jump another power of 10 to reach the estimated total heat flowing through Earth's atmosphere and oceans from the equator to the poles, and another 2 to get the power received by the Earth from the Sun at 174 quadrillion watts. Believe it or not, there's one human technology that has exceeded this level. The AN-602 hydrogen bomb was detonated by the Soviet Union on October 30th, 1961. It unleashed some 1,400 times the combined power of the Nagasaki and Hiroshima bombs. With a blast yield of up to 57 million tons of TNT, it generated 5.3 trillion watts, if only for a tiny fraction of a second. That's 5.3 yottawatts, a term that will come in handy as we now begin to ascend the power scales of the universe. To Nikolai Kardashev, a level 2 civilization would achieve a constant energy output 80 times higher than the Russian superbomb. That's equivalent to the total luminosity of our Sun, a medium-sized star that emits 375 yotta-watts. However, in the grand scheme of things, our Sun is but a cold spark in a hot universe. Look up into southern skies, and you'll see the large Magellanic Cloud, a satellite galaxy of our Milky Way. Deep within is the brightest star yet discovered. R136a1 is 10 million times brighter than the Sun. Now, if that star happened to go supernova, at its peak, it would blast out photons with a luminosity of around 500 billion yotta-watts. To advance to a level 3 civilization, you have to marshal the power of an entire galaxy. The Milky Way, with about 200 billion stars, has an estimated total luminosity of 3 trillion yotta-watts, a 3 followed by 36 zeros. The author Isaac Asimov imagined a galaxy-scale civilization in his Foundation series. Galaxia, he called it, is a superorganism that surpasses time and space to draw upon all the matter and energy in a galaxy. But who's to say that's the upper limit for civilizations? To boldly go beyond level 3, a civilization would need to marshal the power of a quasar. A quasar is about 1,000 times brighter than our galaxy. Here is where cosmic power production enters a whole new realm, based on the physics of extreme gravity. It was Isaac Newton who first defined gravity as the force that pulls the apple down and holds the Earth in orbit around the Sun. Albert Einstein redefined it in his famous general theory of relativity. Gravity isn't simply the attraction of objects like stars and planets, he said, but a distortion of space and time, what he called space-time. If space-time is like a fabric, gravity is the warping of this fabric by a massive object like a star. A planet orbits a star when it's caught in this warped space, like a ball spinning around a roulette wheel. Some scientists began to wonder, if matter became dense enough, could it warp space to such an extreme that nothing could escape its gravity, not even light? With so much power being emitted from such a small area, scientists suspected that quasars were actually being powered by black holes. How a totally dark object can do this has been narrowed by decades of observations and theory. If a black hole spins, it can turn into a violent cosmic tornado. Gas and stars begin to flow in along a rapidly rotating disk. The spinning motion of this so-called accretion disk generates magnetic fields that twist up and around. These fields can channel some of the inflowing matter out into a pair of high-energy beams, or jets. Gas and dust nearby catch the brunt of this energy, growing hot and bright enough to be seen billions of light-years away. Amazingly, the power of a black hole can rise to even greater extremes at the moment of its birth. As a giant star ages, heavy elements like iron gradually build up in its core. As its gravity grows more intense, the star begins to shrink until it reaches a critical threshold. Its core literally collapses in on itself. That causes the star to explode in a supernova. And now, in death, the star can unleash gravity's true fury. In the violence of the star's death, gravity can cause its massive core to collapse to a point, forming a black hole. In some rare cases, the newborn monster powers a jet that accelerates to within a tiny fraction of the speed of light. For a few minutes, these so-called gamma-ray bursts are known to be the brightest events since the Big Bang. 3 orders of magnitude above a quasar, at a billion yottawatts, a 10 with 42 zeros. Remarkably, they are still not the most powerful events known. Albert Einstein's equations contained an astonishing prediction that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. They produce a series of waves that move outward, like ripples on a pond. Scientists are now hoping to detect these gravitational waves and verify Einstein's prediction using precision lasers and some of the most perfect large-scale vacuums ever created. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they are hoping to record the collision of ultra-dense remnants of dead stars known as neutron stars and of black holes. According to computer simulations, as 2 black holes spiral into a fateful embrace, the energy carried by each gravity wave rises 5 orders of magnitude above a gamma-ray burst to 100 billion trillion times the power of our Sun. Does the collision of black holes define the known power limits of our universe? Perhaps not. As turbulent as the environment of a black hole might be, its true power may well lie deep in its core. A black hole's mass is enshrouded within a dark sphere called the event horizon. Since the 1920s, scientists have described the mathematics of the event horizon as the equivalent of a waterfall. It's the point of no return, beyond which water falls freely into the gorge. At the event horizon of a black hole, space itself falls freely in at the speed of light. If the black hole is spinning, then the flow spirals down and around an inner horizon that envelops the singularity. That's the central region where space-time becomes infinitely warped. Any matter that rides this river of space whips around the inner horizon so fast that centrifugal force tends to fling it back out. As that happens, it collides with matter that's streaming in, whipping up a ferocious cosmic storm. The energy of the colliding stream feeds upon itself, rising to what may well be a limit imposed by nature. It dissipates only as it falls into the singularity and disappears. Fortunately for us, gravity walls off such energy extremes behind the event horizon, where they cannot affect the rest of the universe. And so here we sit. Our world is nestled within a vast stream of cosmic energy. somewhere between the spin of an electron and the maelstrom of a black hole. There's no telling whether a future Earth civilization will be able to harness enough energy to advance into the cosmos. For now, as we tap into the tiny morsels of power at our disposal, we venture a closer look at a universe blazing with activity.